So thank you, Katerina. I'll indeed be talking about stochastic gravitational wave backgrounds in very broad strokes, and I'll almost try to convince you that it is a single source, but not quite, not quite. I'll be telling you about current detection efforts, and then I'm going to also try to push into the future a little bit and tell you about what the prospects are with future upcoming detectors. I'm going to apologize for people on Zoom. I'm going to be using a laser pointer. I'm actually going to try not to be using the laser pointer. It's going to happen anyway, but I'll try to be precise. So I'll start by telling you a little bit about the signal of stochastic gravitational wave backgrounds. We'll go through sources. We've seen some of this already, but hopefully it'll be a complementary approach. I'll really be focusing on gravitational wave sources that build up a stochastic background. So in that sense, it's complementary to what we've seen in Kirsten's talk. I'll then be talking about detection strategies, and I'll be focusing on interferometers, ground-based, space-based, because we'll be hearing about PDAs in the next talk. But some of this extends to PDAs, some of it doesn't. Maybe it's nice to bear in mind that there's a connection there. I'll then be moving on to show you stochastic search results from the LIGO-Virgo-CAGRO collaboration, which I'm a part of. And then I'll be closing by telling you about the future, specifically third-generation detectors and LISA. But let's start from the top. What are stochastic gravitational wave backgrounds? So we consider all those gravitational waves which arrive at our detectors but are individually unresolved to build up an incoherent superposition that is then best described by stochastic variables. So it's an operative definition. It's how we search for the backgrounds that uses stochastic methods, not so much that they're necessarily generated via a stochastic process. And now when we try to quantify how much background there is out there, we tend to use this fractional energy density for gravitational waves, omega GW. This is, mind you, a cosmological quantity. It's literally the overall contribution of gravitational waves to the whole energy density of the universe. In fact, it's normalized with this critical energy density rho c. But it's directly related to the intensity of gravitational waves, which we directly measure with our gravitational wave detectors through this simple equation. Note here the scaling, the f to the power of 3 here, which scales between them. So there's some complication there that will come up in a minute. But what I really want to highlight is that by searching for an intensity as opposed to, say, a strain, we're discarding phase information. So the gravitational wave intensity here is a marginalization over the phases. So I'm taking the absolute value of something, and a marginalization also over polarizations because I'm summing over all polarization modes. And that is so overall basically just an energy contribution, right? So I'm looking for an extra contribution coming from gravitational waves in my detector, but I'm not searching for it with anything too specific, so to speak. This will become clearer in a minute. You may or may not have also heard of characteristic strain. So just to contextualize that for you, intensity and characteristic strain are directly related. So characteristic strain, even though it is a strain, is marginalizing over polarizations and phase. And we typically see this in PTA searches, and I'm sure you'll hear about that later as well. So let's dive into what types of astrophysical and cosmological sources source gravitational wave background. You've seen some version of this plot a million times, maybe in this session, maybe even before then. This one specifically comes from a review I'm currently producing. So most of this talk is based on this review. So if anything sounds interesting, do pick it up once that is in press. So the first distinction that we make between gravitational wave sources for stochastic backgrounds is based on redshift. So close by sources, low redshift sources are considered to be astrophysical. And then higher redshift sources far away from us from the beginning of the universe are then instead considered primordial. So let's start with the right-hand side here. First and foremost, I should mention a stochastic background sourced by stellar mass compact binary coalescences, CBCs for short. Stellar mass because I'm looking at this particular area of frequency space. And these are the CBCs that you see directly in the LIGO, Virgo, and CAGRO detectors. So they'll build up an incoherent background. The reason why I mentioned this one first and foremost is because we know it's there, 100%. We're seeing the tail of the Gaussian distribution of the CBCs, and this is the bulk of it, right? So it peaks in the LVK range. So here I'm also showing you how these different detection efforts are probing these signals. It peaks here because there's going to be a turnaround when masses shut off, but then it might also actually contribute in the Lisa band. So this is one possible signal which will give you a multi-banded signal in both experiments. A companion signal to this is the signal from supermassive black hole binary and spirals. So this one is similar in the sense that it's sourced in the same way. You can notice that the spectrum has the same shape, but it's much more massive, and so it peaks in different regions of frequency space. It contributes mostly to the PTA range in its stochastic form, but then, mind you, the actual supermassive black holes merge in Lisa. But they're going to be resolved, and so we're not very interested in them from the stochastic point of view. We're also going to have a stochastic background signal from core-class supernovae. This used to be more in fashion once upon a time, then they didn't detect it, and so now we don't talk about it quite as much, but it should be up here. It should be up in the higher region of frequency space for LVK. And I like to point it out just because maybe one day we'll get rid of all other sources and we'll then just be left with this one to constrain. And then we heard tons on the binary white dwarfs from Kirsten in the Lisa band earlier. So the binary white dwarfs will plague the Lisa band to the point where even though this is a stochastic background, it's actually going to be high SNR, and it's going to dominate the Lisa measurement. It's literally considered a source of noise for Lisa, and it will mask out all the other signals. So, look out for this one because it's going to be tough to get around it. Going on the other side of things, thinking about primordial backgrounds. Well, the first one that comes to mind is, of course, the gravitational wave background sourced by the end of inflation. What I like to point out about this one is that you'll see that after it sort of dials down, peaking at higher frequencies, it then scales constantly for the rest of the frequency space. And this is because we expect it to become scale invariant. So it'll be produced when the universe is small and just becomes bigger. And then it just freezes in size and remains scale invariant for the rest of the evolution of the universe. And it's usually, it's mostly probed by the CMB in the sense that the CMB measurements of the temperature fluctuations will constrain gravitational waves in the lower end of the frequency spectrum. But of course, in principle, you could constrain it with all the measurements just because it's on. It should be on at all frequencies. A really tricky one to nail down are the first order phase transitions. These are transitions that would happen in the primordial universe. And there's so many models for these things. I could spend an hour talking about just that. But the point is that most of them will have a characteristic peak, and this characteristic peak is linked to a frequency that is directly related to the temperature of the universe at the time the phase transition happened. So if you don't detect a peak, there was no phase transition at that temperature. If you do, there was. So it's really a nice and easy link and it's a very direct window into early universe. And another one is cosmic strings. So cosmic strings are linked to phase transitions, but the background from cosmic strings is sourced by the snapping of these strings in the primordial universe. So in a certain sense, it's similar to a CBC background in the sense that it behaves as pops or as shot noise. We'll get more into this in a minute. And finally, primordial black holes. So primordial black holes, it's primordial black holes, so it has to go in the primordial section, but they do behave like the stellar mass black holes for much of their lifetime, right? So it's going to be a signal that is similar to the stellar mass CBC background, and maybe picking them apart is going to be a challenge. So these are all interesting things to investigate. Okay, so I've gone on about that enough. Let's just, for one more moment, zoom into the CBC background that we constrain directly with LIGO. So these are black holes and neutron stars. And this is fresh off the press. So I really had to show you. So these are updated results from the GWTC3 catalog populations paper. It came out last week. And these are the projections of what we expect the stochastic background to be based on the direct measurements that we have of merging binary black holes, binary neutron stars, and mixed neutron star black hole binaries. So the uncertainty here is given by Poissonian uncertainties around the merger rate, and also for the black holes, the uncertainty that we have on the mass spectrum. And then you can compare this with how we do in sensitivity with the ground-based detector network. In black, you have the current sensitivity, the O3 sensitivity. You'll see we're about an order of magnitude shy of the signal. So we're not detecting it, and we know we can't detect it. So in that sense, we're all good. But we would like to detect it. And so can we? Well, potentially, right? So these are the future curves. This is design sensitivity, design A+, future configurations of the ground-based detector network, not too far away in the future, which we hope to achieve. Okay, and so those would start to dig into the signal and give us a positive detection. So this is going to be really exciting science in about a few years. So let's dive into the characteristics of these backgrounds, specifically pertaining to how we go about detecting them. So one interesting thing to look at is how do these backgrounds behave in the time domain? So specifically, are these backgrounds Gaussian, or are they actually non-Gaussian, i.e., in the time domain, this translates into are they continuous, or are they intermittent, or popcorning? So a background from CBCs, especially given what our knowledge of the stellar mass CBCs we have with LIGO Virgo, well, we know that there's going to be a pop once in a while. It's a single signal in the sense that it's the accumulation of all the subthreshold signals, but they're still going to be very sparse in the time domain. You can isolate them, and if you're really, really good, maybe you can actually get more information out of each individual signal, say if you come up with a really nifty algorithm to do that, right? Whereas as you start getting more and more signals overlapping, you get to a fully Gaussian limit down here where you can't pick signals apart in the time domain. There's nothing you can do. They completely overlap. And this gives you a fully Gaussian limit. This is really well described by a Gaussian distribution. So depending on how your background behaves in the time domain, you want to be searching for it with a different recipe. And we'll be seeing this in a minute. Another feature is how does the background behave as a function of direction, okay? So typically, maybe at a first approach, you might assume this background is nice and isotropic, say like we did for the CMB. But then you can start thinking about, is it actually anisotropic? How is it distributed as a function of sky location? So for the most part, for gravitational wave backgrounds, we assume that they're actually statistically isotropic. Again, think of the CMB. It was first isotropic, and then it's statistically isotropic and actually starts to get some fluctuations, but they're the same. Each direction you look at, they're described by the same angular power spectrum, and that's what we're looking at here. So this is a projection of the angular power spectrum that we expect to see this is specifically a binary black hole background. And these are two different projections from two different groups. They actually don't agree particularly well. So I think the take-home message is it would be great to measure this and find out what's the truth. But beyond this, I should also point out that background, for example, from the white dwarfs that you see in LISA will be very specifically anisotropic and well described by the shape of the Milky Way. So there's also steps that you can take to go beyond just describing it with an angular power spectrum alone. Okay, so moving on to detection methods, how do we actually search for stochastic backgrounds? Now, I'm going to try to take it slow because there's a bit of maths, but you guys are all well-versed in maths, so that's good. And I'll try to highlight this cross-correlation statistic because it features every which where in stochastic searches. So cross-correlation statistic between different detectors. If it's the same detector, you can think of it as an autocorrelation statistic, but this is really the way that we represent the data that comes up everywhere when we do stochastic searches. But let's start a step back from that. What do the detectors actually measure? I think Katerina flash this at the very beginning of our session today, gravitational wave detectors collect time stream data, so this is time domain. And our basic assumption is that the time stream data will have a pure signal component and a pure noise component. Now, if you don't have a good model for your signal, so if your signal is a stochastic background and all you know about it is it's stochastic, and all you know about the noise as well, it's also stochastic, how do you pick the two apart? And this is the whole basis of stochastic searches. So what you do is you come up with ways of getting rid of the noise, for example, by assuming that the noise is completely uncorrelated by two detectors. So what you can do is you can construct the cross-correlation of already FFT'd to the frequency domain, because we know that the noise is nice and diagonal in the frequency domain. Tyson pointed this out earlier. So it's nice and easy to work in the frequency space. And then we have a statistic for the cross-correlation. We expect that the cross-correlation of detector 1 and 2 will give us a measurement of the intensity of gravitational waves, because the noise is not correlated, so it won't contribute to this estimator. And what features here are how the particular detectors respond to the background signal. So R1 and R2 are the specific responses of detector 1 and detector 2, but you can actually just look at the cross-correlated response, so the overlap response of the two detectors. And this is scaled by the time of observation, because the more you observe, the more you narrow down to this, because the noise is averaged out, right? The random correlations between the noise will start washing out. And you can jump to the omega parameter for gravitational waves. Most of the results I'm going to show you today are actually in terms of omega through the initial equation I showed you at the very beginning of this talk. So again, the cross-correlation statistics takes you straight to the omega parameter of for gravitational waves, again scaled by this f to the minus 3. So what do these overlap functions, these overlap responses look like? Here I'm giving you a collection. I'm showing you LISA, LVK, so samples of the LIGO, Virgo, and Kagra response functions. And this is somewhat related to the Hellings and Downs curve for PTAs. I'm sure you're going to hear tons about that later, but it's just, I'm planting that seed. And so what can we investigate specifically in the ground-based network, and how does that compare to what we see from space with a single detector, which is LISA? So in the ground space, we actually operate in something that we call a small antenna limit. And that means that the arms of the detector, the arm length of the detector, or the scale of the detector, I'm just representing it with just a generic L, is much smaller than the wavelength of the gravitational waves that we're probing throughout the measurement. And so that means that the arm transfer function, so the way that a single arm is geometrically sensitive to gravitational waves, is completely frequency independent. It's constant throughout frequency. So the modulations you're seeing here in frequency are actually all due to a phase factor that boils down to a dependency on the baseline length. So each of these baselines, the Hanford-Livingston baseline, the Hanford-Virgo baseline, and the Hanford-Kagra baseline, they all have different lengths. And so they will all have a different contribution to the sensitivity to the background at different frequencies. And the modulations you see here are modulations given by this phase term that scale, that because the baseline couples to the frequency, this will give you this damping factor at higher frequencies. So stochastic searches, you can see, while they're quite sensitive at lower frequencies, they're actually quite insensitive to signals at higher frequencies. So this already shows you, if you remember what the LIGO sensitivity curve looks like, this is telling you that the nice space above a few hundred hertz, which we'd like to probe, is actually suppressed in stochastic searches, simply because the Earth is only so big. If the Earth were bigger, if we could put detectors further away from each other, then we could access those modes. But because the Earth is very compact and we're limited by the baseline length, this is what we get. And the story is even more different in LISA. LISA is just one detector, so in principle, how do you even do a cross-correlation statistic? Well, you can correlate, autocorrelate, or cross-correlate different channels in LISA. I'll maybe give you a few details later on. But in principle, this is not a small antenna. This is actually a large antenna because the arm length, so the arm length is the distance between the two spacecrafts and the laser is bouncing between them. The arm length is comparable to the wavelength of the gravitational waves that we're probing. So what that means is that the arm transfer function is actually modulated by the interplay between the arm length and the frequency, and these zeros are where you have an exact fit between the wavelength and the arm length, right? So you have these sinks. In fact, it is a sink function. And you will have a different sensitivity to gravitational waves depending on how you arrange the arms, how you consider the arms to interact. So that is what we get with LISA, and in particular, you see that we get more and more and more modulations at higher and higher frequencies. So this is actually where a lot of action comes in for stochastic searches. Okay, so let's start by discussing how we search for the easiest, so to speak, signal that we could possibly come up with. So a signal which is both Gaussian and isotropic on the sky. Now, the Gaussian assumption applied to our data is just, well, we just assume that the data is is well described by a zero mean Gaussian variate. And so we write down a likelihood which, I don't know, if you just at a glance, it almost seems like there's no information in there at all, right? The one that Tyson wrote down earlier, you had a D minus H, where H was your model, and that's where your parameters come in. Where do the parameters come in for a stochastic search if everything is just average zero? Well, they come in the data covariance, right? So the data covariance is effectively our cross-correlation statistic, and that is where the intensity of the gravitational wave background features. So all the information that we're interested in is captured in the covariance, and then we assume that the noise covariance is actually well measured by the autocorrelation of a detector. Now, if we start thinking about what we do in LVK, so in ground-based detectors, we actually are working in a low signal limit where the autocorrelations, which would feature in this likelihood, are actually just measurements of noise and they're only going to bias our estimate of our signal. They're not actually giving us any information about the stochastic background itself. So what we can do, and this was done recently by Battis Romano, so this was this year, they actually proved this analytically, but we've been assuming this all along, so thank God it's true. We can actually use the likelihood in the cross-correlation statistic itself, and what we're assuming is Gaussian is the residual of the cross-correlation of the two measurements minus the model that I showed you earlier. So it's not the same assumption completely, right? If this is Gaussian, if this is Gaussian, not necessarily this is Gaussian, and in fact, this is only true if you average over a lot of frequencies and a lot of times. And because we do operate in that regime, then thankfully it all works out. And you can take it a step further and formulate this in terms of a Bayesian approach. So you can write down a likelihood of taking the log of it in omega directly. So omega is exactly the parameter that we're trying to constrain, or it's the signal, the parameters of which we're going to try to constrain. And we know it's directly related to the cross-correlation, so we just plug all that information in. And now the way we formulate this is we formulate it based of where this is the data, the measurement that we're making with the cross-correlation, and we're comparing different models to the data, exactly like Tyson was pointing out at the beginning. Only now all of this is in terms of a squared quantity of the strain, of the phase averaged quantity. And so models that we can stick in here are just gravitational wave background signal, plus some uncorrelated noise. So basically, it's just the signal if you take the cross-correlation. You can also do something more fancy. You can start looking for, is there a signal plus some other correlated noise that I know of, plus some uncorrelated noise, or just correlated noise and uncorrelated noise? There's lots of different ingredients that you can plug in here. So this is an incredibly flexible tool to test whatever you want. And that is what we do in stochastic searches with the ground-based detector network. So an important role here is what happens in frequency space along all this. As you noticed here, I'm integrating over frequencies. So what do we know about the signal in frequency space? And it turns out we we can make and then break a whole set of assumptions when it comes to the spectral shape of the background. So what we usually assume, and I want to say almost exclusively assume, is that we can take the background to behave as a power law in frequency. If you remember the plot I was showing you at the very beginning, most of them were basically power laws, so it holds quite well. We actually have searches that don't do that. They do a binned narrowband fitting, but for the most part, the flagship searches kind of focus on this approach. And then we also do something in between where, yes, we say that this is a power law, but let's fit for the parameter of alpha. Let's fit for the spectral index as opposed to fixing it. But if you do choose to fix it and do something, the first approach that should give you a detection if something is actually in your data and is behaving the way you think it should, you can literally just fix a power law and search for it in the data. So typically we search for 3 power laws. One is alpha 0, so associated with a cosmological background, it would be the flat background in omega. If you remember those f to the -3, that's where this tilt is coming in from, because this is the intensity of the background as opposed to the fractional energy density. If you have an in-spiral dominated background, we know from GR and so forth that alpha should be of a value of 2/3. So this trickles down into this shape. And instead, if you want to do something, you might consider it more agnostic. You might consider it a bit cheeky, depending on who you are, of a best fit approach. So what is the spectral shape that is best described by the data? Then you can take a flat spectrum, which would be alpha equals 3, which cancels out that -3 in the conversion between intensity and omega. And what I want to point out is that the place where these spectral shapes connect to for example, the LIGO sensitivity, the LIGO noise PSD, is at a very specific frequency that is going to be the frequency that is most sensitive to the background that behaves that way, right? So here, this is around a frequency of 25 hertz. So all of our measurements are actually, we say they're made at 25 hertz where we're most sensitive, and then we assume that if this is the shape of the background, we're actually making a measurement in all frequency space. But that's just because we think we know what's going on in the spectral shape. So we can relax that assumption. So let's start. Let me take a quick break, and then maybe. OK. So we can relax the assumptions one by one that we made at the beginning. And so one thing that we can relax is let's actually think of an anisotropic background as opposed to an isotropic one. What will change in my likelihood formulation? And well, not much has to change. You just need to add directional dependence in your model. So in your cross-correlation statistic, you can add a directional information. Your overlap function now becomes a function of direction as well. And in fact, the detectors sample the sky in different ways. So this is actually going to give you a lot of information about what's coming from where. But this will add a lot of parameters to estimating your model. And in fact, we don't usually do a Bayesian approach to this because it's a lot of parameters to handle. And these parameters will be, for example, pixels. If you're pixelizing the sky and trying to figure out what is the intensity in each pixel, you might do it in the spherical harmonic domain, which is just the conjugate space. But again, you're left with a lot of parameters to constrain. And the information that you have on these parameters can be quantified in a Fisher information matrix. So this is the maximum likelihood solution you get. If you take that likelihood at the beginning, shove in some directional information, and then maximize it. So you get a Fisher information matrix that is telling you how different directions on the sky correlate throughout your measurement. And then if you invert it and apply it to a projection map, so this is the data projected onto the sky throughout your measurement, you get a map for the intensity of gravitational waves. And the tricky bit, though, is that because you do not have a lot of information, you don't know exactly how different directions correlate, inverting this Fisher matrix is actually really tricky. So to give you an idea of what the overlap function looks like as a function of direction, this is what it looks like for the Hanford and Livingston pair at a given point in time. So here we have this hot direction, this direction where we're maximally sensitive given this detector setup, and then some areas where we're least sensitive. And this is time dependent because the pair of detectors will scan the sky as the Earth rotates on its axis with respect to the background that instead is not moving with respect to the measurement. And hopefully it'll start moving, yes. So throughout the day, this is in galactic coordinates, you see that the hotspot samples the sky. There's an area of sky which you're sampling more and more, and this is giving you lots of information in your Fisher matrix. There's also whole regions of the sky you're not even looking towards. And those are going to be holes, zeros in your Fisher matrix. And that's what the Fisher matrix then looks like. So you have a discrete amount of information. It's kind of focused along the diagonal, but then you've got lots and zeros. I'm sorry about the colors here. They're not showing up particularly, but this, I think we can all agree that the dominant color in this color map is this one, which is 0, which means that inverting this is hell. And the ways that you can get around that is either, you can sample for more and more time. You just observe for a long time. But there's a degeneracy, right? Because the Earth rotates along one day. After a day, you're not accumulating that much more information if your background is stationary. But the other thing you can do is add detectors. So if you have more detectors, they're going to be looking in different directions here. So imagine adding lots of hotspots here, and that will start to oversample your Fisher matrix. The other assumption you can relax is, well, what if the background is not even Gaussian? So we saw that at the beginning. I showed you that the background will have some certain time dependence. And if your background is given by a bunch of intermittent compact binary coalescences, the assumption that it's going to be a nice and continuous Gaussian background in the time stream is completely false. So let's take a step back and think of, well, if we know that it's a background of CBCs, we can write down the likelihood for a single CBC. So a data segment that has a CBC might have a likelihood that looks like this, where H1 is then your deterministic model for your compact binary coalescing, and you can search for it by using this likelihood. But then if you know that sometimes the signal is on, sometimes the signal is off, you can write down a Gaussian mixture model, which has both the signal likelihood, so something that looks like this, plus an empty likelihood, a noise likelihood, which will be something that looks like this, where HI is just 0 because it's a mean zero Gaussian. And the ratio between signal and non-signal, the Gaussianity parameter, if you will, is parameterized by this psi, which is a duty cycle, right? So if it's normalized to 1, it's literally the probability of there being a burst of gravitational waves at any given time in your detector. So this is nice and simple, right? And how do you actually apply this to real data is a tricky question, and it can get hairy in no time. And the way I think about it is you ask yourself, well, am I going to use really a deterministic model to model these bursts? So if you say, yes, absolutely, I'm going to use a CBC waveform, and in each little segment of data, I'm going to fit this waveform to the data and say, do you have a CBC in it? Well, then you're going to do something like the Bayesian search, which was first formulated in 18 by Smith and Thrain. And here you know a lot about the signal. You know that it's binary black holes merging. Let's use that to the max. It is the optimal search for this style of background. And it's the natural continuation of the CBC searches that we already do, only we only do them where we have triggers because we know, oh, there's a high SNR trigger there. Let me go and investigate it with a deterministic model. You can relax this a little bit and say, well, let me search for a stochastic burst instead. So I know there's a burst. I'm actually only interested in knowing how much of that energy that I'm measuring is gravitational waves. So you can basically recycle everything you know about the cross-correlation statistic in the Gaussian mixture model context and come up with an intermittent stochastic search. So you're just looking for correlated bursts between detectors, and you know that there should be no correlated burst if it were only noise. And this was formulated. The outline of this approach is quite old. It's almost 20 years ago by Drasko and Flanagan, but we've actually started working on this again recently with collaborators, and hopefully these will be sort of complementary approaches in the end. So how am I on time? I'm OK. So this is the second part of my talk, where I'm going to show you some search results from the LIGO, Virgo, and Kagra collaboration. So just to remind you, it's these 3 detectors on Earth. And because we're stochastic, we're more interested in the baselines than the detectors themselves. So if you imagine that you have these 3 baselines, where one is is shorter, the one in the US, and then you have 2 longer baselines that connect the US detectors with Europe. And this is the most recent isotropic search paper. So this is using all those tools that I showed you before for the isotropic Gaussian search. The new addition of Virgo features here. These are the first set of searches with the O3 data that feature the extra detector. Extra detector means 2 extra baselines, which is very important for stochastic searches. And I like to divide this up into sort of 3 categories. We have a focus on CBC backgrounds, where we're setting upper limits by modeling with the alpha 2/3 power law, and we're really zooming into a CBC background. Let's see if we can detect it there. And then we also combine this stochastic search with the resolved searches to get an updated measurement of the merger rate of binary black holes as a function of redshift. So the stochastic search gives you a measurement of the merger rate at high redshift, whereas the resolved the resolved sources give you a measurement at low redshift, and you combine them in a Bayesian framework and get a fully informed merger rate. We then do an unmodeled search, if you will, so you can simultaneously fit for the spectral index and the amplitude of gravitational wave background. So that is also in this paper. And then you can take it, and run with it. You can go and test whatever models you want. The models that we present in this paper are non-GR polarization modes, and also, is there correlated magnetic noise coming from the magnetic field of the Earth that leaks its way into our detectors. So specifically, just to flash this, the colors are terrible, I'm sorry about that. The number that we get, so the upper limit that we put on a background that is dominated by compact binary coalescences is this number here. So it's a very small fraction, about little over 10 to the -9. And it compares kind of unfavorably with what we expect this background to be from the second slide I showed you from the recent Rates and Pops paper. So we expect this background to be about an order of magnitude less. If we're lucky, it could be a little bigger, and so we could detect it a little sooner. But it's the interplay between how this is going and how this is going that is going to tell us how long it's going to take to detection. So let me flash a few numerical results. This is the cross-correlation spectrum from the combined 3 baselines in O3. This is literally the cross-correlation statistic. And what you'll notice is it's nice and symmetric around 0, so you're not measuring anything. If you had a signal, there would be a bump. And so this is a check, a reality check that everything is mean 0 and Gaussian. And effectively what this is just the noise. So all the lines you're seeing in here are the noise lines, and we know where they're coming from. And these are the posteriors on the alpha parameter and the omega parameter of gravitational waves. This is using a log uniform prior. We actually have a version of which has a uniform prior as well. And again, you see that this is nice and consistent with 0, and so is alpha. So what we say is we're really not measuring anything but the noise here. This is how the noise behaves. Alpha equals 0 is how the noise behaves in the detector. And then we combine this with the binary black hole merger rate that we get from the direct detections of CBCs, and we get this beautiful plot, which is the merger rate. These are each posterior sample of the merger rate as a function of redshift. It's a lot to take in just a second, so maybe I'll break it down for a minute. We can parameterize the merger rate of binary black holes as a function of redshift like this. So this is just some analytic function, and you have 2 exponential parameters, this alpha and beta, that determine what's the slope here and what's the turnaround, and then you have a z peak, which is the redshift at which the turnaround happens. So The direct detections give you a lot of information about the slope down here, so that's the alpha. So we know very well, and you can see it's very well constrained, what this slope is. And if you had a measurement or a non-detection even of a stochastic background, you'd know what it looks like on this other side. And you see, because we don't have a detection and our constraints are kind of weak compared to the CBC, the direct CBC detections, this then just becomes a hot mess down here. So the two measurements are really complementary in this framework, in the sense that the measurement of a stochastic background will give you a good estimate of Z peak. And so we could start and rein in this dispersion that we get at higher redshifts. And the other half of this plot is the actual posterior distribution that you get. So this is what really tells you, oh, actually, most of the information here is coming from the direct detections of CBCs as opposed to the stochastic search itself. Because if you had a detection of the stochastic background, you'd get this solid black line here. And this is what is telling you that if you do not detect it, everything up here is sort of excluded. But you see that we do a much better job if we include the CBCs from the direct searches. So what we know right now is that the stochastic search isn't contributing that much. The hope is that it will. And knowing whether it will or not is sort of an open debate. It really also depends on the depth that we can observe CBCs with our direct deterministic measurements. Let me whiz through the anisotropic search, because I do want to say a little bit about the other detectors as well. We do anisotropic searches with the method that I described earlier. We typically divide them between broadband and narrowband, whether we're integrating over all the frequencies or whether we're binning in frequency. And we also divide them between, this is a bit of an unhappy wording, but whether it's a radiometer search or a spherical harmonic decomposition search. The names are not entirely transparent, but the spherical harmonic decomposition search does use spherical harmonics, and the radiometer search instead uses pixels. And what that translates to, these are the results from the latest paper from this year, is that if you're using the pixel space and you're doing this radiometer search, the assumption, for some reason, which is not maybe entirely transparent, but please give me a little bit of leniency, the assumption that we make here is that each direction is completely uncorrelated. So the way to interpret these maps, which are SNR maps, and you can see we don't have any high SNR signals in here, is that each pixel is a single source. This is the SNR that you get if you think that all the measurement you're making comes from that particular pixel. So to obtain these maps, you don't really need to invert the full Fisher matrix. You're assuming a priori that your Fisher matrix is actually diagonal in terms of the signal. And so any off-diagonal correlations in the Fisher matrix are not contributing towards your measurement of a signal. They're just noise. Okay? And so that's how these maps come out. A different story is what we do for the spherical harmonic search, because in that case, we do assume that there are correlations, interesting correlations on the off-diagonal terms. And we use spherical harmonics because they're better to describe broader regions of sky all at once. And we can reduce the number of degrees of freedom by cutting down in the number of modes that we accept and just look for broad correlations on the sky, say like a dipole, which would be a very broad correlation. So there we do use the full Fisher matrix. And to invert it, we use SVD techniques, singular value decomposition, and also the fact that we have an extra detector, 2 extra baselines, fills in those gaps in the Fisher matrix very nicely. And these are the upper limits that we put on the angular power spectrum. And then we do also put other constraints on lots of other interesting models. I just wanted to shout out to Cosmic Strings, because this is a really nice result, and it was featured in PRL this year. So we put a very strong constraint on the cosmic string tension, because the cosmic string tension is directly related to the omega that you'd then get. And also primordial black holes, because we do not detect a stochastic background of primordial black holes, we can exclude that cold dark matter is completely made up of primordial black holes. So that is also a pretty neat result. And we also put constraints on first order phase transitions and other very interesting things, which these are all clickable links. So if you download the slides, they'll open up a plethora of interesting papers. So with the remaining time I have, let me take you through future prospects. Am I really bad on time? Okay. Okay. Sorry about that. I haven't given a live presentation in a long time. So the upshot of a future 3G detector, so Einstein telescope and cosmic explorer, is that potentially we will see binary black holes at really incredible depth. So the expectation is that we'll actually resolve all the black holes. So there's not going to be a stochastic background from black holes. It's all going to be directly detected. So this is, these two curves, the black and the red, are the expected sensitivity curves with CE and ET. So what is there left to do for stochastic searches? Well, there's plenty of interesting things. We can still worry about binary neutron stars and black hole neutron stars. We actually get a lot of interesting things for primordial black holes because maybe we could actually pick them apart. These primordial black holes are expected to dominate the very, very high redshift, which is not accessible still. So if we do have a stochastic background that behaves like a black hole background, it could be primordial. And then lots of cosmological backgrounds. But what this means is that we will start to worry about separating out these different sources of background. Up to now, I've told you about searching for one source of background at a time. And we can worry about how to pick them apart. We can either do that by subtracting, do an iterative subtraction of the high SNR backgrounds and just do step by step until we narrow down to the lowest one. Or we can try to simultaneously estimate them in a Bayesian framework, and this was done also recently, and sounds like the best thing to do if you have competing signals. Finally, let me talk a little bit about LISA. I hopefully have convinced you somewhat that LISA is a very different challenge compared to the ground-based detectors, specifically in the stochastic framework because we're not in the small antenna limit. It's also just one detector. So we're mostly making measurements with the autocorrelations that brings with it a whole new bag of issues that has to do with how we're going to deal with the noise in the detector. And the way that the measurement is constructed itself is completely different. We use time-delayed interferometry. So each link measures gravitational waves in some way, each link is sensitive to gravitational waves in some way, but to make the measurement, we need to combine the links. And the way we do that is up to us. So there are plenty of studies to figure out how do we combine these links to get the best measurement, or the least noisy measurement of gravitational waves. And say we wanted to add a detector to get higher angular resolution, more sensitivity to gravitational waves. Well, that's pretty challenging to do in space. Lots of proposals to go through. So we cannot rely and just say, well, we'll get extra detectors in the future that'll do the job. So I just wanted to show you what the overlap function for gravitational waves for LISA, for an autocorrelated channel in LISA, looks like in frequency space. Because I showed you at the beginning, we're not in the small antenna limit. So there's lots and lots of modulations that come into this frequency response just as you go up in frequency. And you see that as you go higher and higher in frequency, the response pattern on the sky changes dramatically. So this means that we need to be really careful with how we model the response. It also means that potentially if we use this modulation to our advantage, we can glean more information out from the background. And the way we do that is pretty much along the lines of what I described before. We're using the same shape of likelihood, but now instead of using the strain measurement directly, we have to combine these channels. We have to combine the link responses in channels, and we might even go as far as using the diagonal space for the noise of these channels, because there's going to be a silent channel, a Sagnac channel, which is insensitive to gravitational waves, but then that might mean that we can have an independent measurement of the noise, which we then use for the autocorrelated measurement, and that aids in all our measurements. And I'm going to skip the angular resolution and just thank you for your attention.